All right, so now let's go into the particular functional groups that I want you to be able to identify, okay? First and foremost, the CH bond. So this is obviously going to be one of the most common that you're going to see in just about every IR spectra, or every IR spectra you take, because just flip back in your notebook, right? How many compounds that we've seen have carbon and hydrogen bonds, right? That's kind of the name of the game in organic chemistry. These are going to fall in this region here, right? Bonds to H, so between 2,700 and 4,000, okay? So there's three different possibilities that we can have with our carbon-hydrogen bond. By far the most common is going to be the sp3 carbon-hydrogen bond, right? So we'll see that these change slightly depending on the hybridization of a carbon. So an sp3 hybridized carbon bound to a hydrogen will absorb around 2,900. This is going to be the most common one. You're going to see this in every IR spectra you take, just about. If it's an sp2 carbon hydrogen bond, this is going to absorb above 3,000 at about 3,100. And then if it's an sp carbon hydrogen bond, this is going to be even higher. Okay, so we can use, especially this and this is the most important in terms of identifying functional group. It'll allow us to detect whether we have a double bond, an alkene, or if we have a terminal alkyne. Okay. Yeah, and again, the reason why those two are sort of more important than this one here is because this is going to be in just about every spectra you ever see. Okay, so again, the carbon-hydrogen, the sp3 hybridized carbon-hydrogen bond is going to be in just about every spectra you see, and you're going to see them between 2,850 and 3,000, and it's going to look like this. It's going to be this cluster of fairly narrow peaks, but you got a lot of them kind of sitting right on top of each other. Okay, and so you notice what they, well, so just to continue here, so that's going to be in just about every spectra, this cluster of peaks. It will end before 3,000. That's going to be an important way that we're going to be able to distinguish between alkanes, alkenes, and alkynes. The absorption tends to be from medium to strong. So if you have another functional group present that's really, really strong, they can be on the medium side, but they're going to be pretty large. And again, you have a lot, they're narrow peaks, but there are a lot of them stacked kind of right next to each other. So they merge into this like big, ugly block. Okay, so one of the things that we're going to do when we analyze our spectra is we're going to lay down this line at 3,000. And the reason we're going to do that is because if there's anything north of that, anything higher than that, then that corresponds to either an alkene or an alkyne. Okay, so if you have an alkene, that's a peak that sits at around 3050. Tends to be on the lower end of things. It tends to be smaller than the sp3 carbon hydrogen bond, but it's nice and very narrow, right? So again, we draw that line at 3,000, and if there's a peak sitting just north of that, then it's an alkene. Okay, again, around 3050. Unfortunately, what you're going to see from sample to sample is, you know, hexene might be 3080, whereas pentene is 3070. It can kind of fluctuate a tiny bit. So don't take the 3050 as exactly that, right? So unfortunately, there's some experimental wiggle room here. But that's why, again, what you're going to do is you're going to lay down that line at 3,000. And if there's anything just north of that, that's going to signify to us that it's an alkene, or there's rather that there's that sp2 hybridized carbon hydrogen bond. So notice here, this would be a compound like something like butene, where you have these sp2 carbon hydrogen bonds here, but you also have a ton of these sp3 hybridized carbon hydrogens. So we still have that big ugly peak just south of 3,000. An alkyne, very similar. So again, what we're going to do is we're going to lay down that line at 3,000. If we have an alkyne, and it has to be a terminal alkyne, note, right? Because it has to be, you got to have that carbon hydrogen, sp carbon hydrogen. So that'll only be for terminal alkynes. But that's going to be one that sits a good bit north of 3,000, around 3,300. Still going to be nice and sharp, and tends to be on the medium to strong side. So again, this would be a good example of a compound that might have a spectra like this. still has all these sp3 carbon hydrogens corresponding to this big ugly peak south of 3000. But then now we've laid down our 3000 line and we see this sharp peak just north around 3300. Okay, so those are our alkane, alkene, and alkyne carbon hydrogen bonds. Again, just to stress, we're talking about carbon hydrogen bonds, right? So if you have a fully substituted alkene, for example, here, there's not going to be any sp2 carbon hydrogen bonds going on, so you're not going to see any signal around 3100. Likewise, if we have an internal alkyne, right? If it's not a terminal alkyne, then we're not going to have any sp carbon hydrogens. So we're not going to get a signal around 3300. Double and triple bonds, okay? So again, when we go to our spectra, what we're going to do, we're going to make that line at 1600 and we're going to completely ignore everything south of that. That's the fingerprint region. And then you're going to go through and you're going to cut your spectrum up into different places. The first one that we're going to talk about is, so we talked about carbon hydrogen bonds just because they're pretty ubiquitous. But the next segment you want to look at is between 1600 and 1850, right? So when I get my IR spectra, I'm immediately going to put lines at 1600, between 1600 and 1850. If there's anything in there, I know that my compound has a double bond. We'll talk about carbonyl groups in particular here in a second, because they're like a super obvious, awesome signal that you can pick out. They're pretty easy to see. They're nice and strong and narrow. Carbon-nitrogen double bonds are quite a bit more rare. There's like only a few compounds that you would ever deal with that have those. So suffice it to say that they would still fall in this region. They would be on the medium to narrow side. But honestly, I'd be surprised if you ever came across one. So the big one to pick out are carbon-carbon double bonds. Okay, these are going to be on the medium end of absorption. They're not crazy strong, but they're not crazy weak. They are nice and narrow, and they'll sit at the lower end here. So between 17 and 16. Okay, the higher the electronegativity between those two atoms, the more it'll shift up. So we'd expect the carbon-nitrogen double bond to be slightly higher than that range, carbon-oxygen double bond slightly higher than that range. Okay, but yeah, so that'll be a peak, and we'll see an example there. You can also, if you have a benzene ring, there will be this carbon double bond. However, they are terribly weak peaks. And sometimes you can't even really see much at all, except for what we call overtones, or like barely some like weeds in the grass there. So I don't really use this double bond region to assess whether I have a benzene ring. I'd instead look at the sp2 carbon hydrogen region to assess that. Because again, the carbon-carbon double bond in a benzene ring just doesn't give you a very good signal. I think people who are super trained in IR can spot these a little bit better. For me personally, I don't think it's very easy to spot the benzene ring in this particular region. So let's look at octene versus octane and see how those spectra would compare when we overlap them. Well, again, what we're going to do, we're first going to mark it off, around 16. We're going to discard everything that's going on in the fingerprint region. And then that 16 to about 1850 is where we would expect to see peaks if we had a double bond. So we indeed get our carbon-carbon double bond peak here. Okay, and you can see it's like a bit of a medium absorption peak, but nice and narrow. And then another awesome way to check is we would have our sp2 carbon hydrogen bond. Again, how do we spot that? We lay down that line. I can actually probably do this. Lay down that line at 3000. And then we see a peak that's just north of that, corresponding to our sp2 hybridized carbon hydrogen bond. Okay. Triple bonds. So triple bonds are going to be in the 21 to 2300 peak. So again, it's all about like going in and putting down bars on these graphs and saying, do I have a peak in here? The two most common, really, I think the only ones that you're going to see for triple bonds are carbon-carbon triple bonds. For an alkyne, those are going to be between 21 and 2200. Those are, again, nice sharp peaks. They tend to be on the medium side of absorption intensity. And then you have nitrile carbon nitrogen triple bonds, so a cyanide group. They absorb in the 22 to 2300 region, so a little bit further up, and they are strong absorbing peaks. So again, very narrow, but the big difference between carbon-carbon and carbon-nitrogen is A, the wave number that they absorb in, but also the magnitude of that absorption. A nitrile group has a much stronger absorption than an alkyne triple bond does. So just to look at two examples of that. So again, sort of the name of the game, we're going to go through and put in our 21 to 2300 lines, 21 to 2300. So we can see up here, we got peaks in both of these spectra in that region. So that's indicative of the triple bond. Here it's on the lower end of that range, around 2120. And it's a medium absorption, maybe even a little bit on the towards the weak end. So that's going to be a alkyne carbon-carbon triple bond. And then if we look at the bottom one here, that's on the higher end of that region, right? So that's around 2250. And it's a nice strong absorbing peak corresponding to that nitrile group. Just to point out up top, we can actually even determine that this is a terminal triple bond. Because again, I lay down that line at 3000, and what do I see? I see that sharp peak sitting around 3300, indicative of that carbon, the sp hybridized carbon hydrogen. Alcohols, probably the easiest functional group to spot. This right here, a nice broad peak. Whoops, I'm still in this mode. A nice broad peak between 3200 and 3600. Strongly absorbing and incredibly broad. That's the signature of an alcohol. So again, the whole name of the game is like being able to look at these IR spectra and be able to identify functional groups in a molecule. If your molecule has an alcohol, you would expect a nice broad peak that's really strong up at the in the 32 to 3600 region. Notice here, right, what do these peaks correspond to? Those are all of these bonds here. Our sp3 hybridized carbon-hydrogen bonds. And then you can see, though, there's some CO stretches down in this region. This is, again, in the fingerprint region, which we do not care about at all. I mean, again, there is absorption going on because of carbon-oxygen, but it's just incredibly hard to distinguish from carbon-carbon absorption. It's one of those things that, you know, if you knew after the fact, great, but if you were just given this spectrum, it'd be really hard to point out that that particular peak is a carbon-oxygen bond. All right, carbonyl group. So this is another one that's really easy to spot right off the bat, and that's because it has this wonderfully super duper sharp, super duper narrow peak that sits almost always exactly at like 1720. So between 17 and 1750, you will have this super strong, super narrow peak indicative of a carbonyl group. So notice that is in our, we said double bonds were 1600 to 1850. That's in that range. But out of all the double bond peaks, these are by far the easiest to spot, mainly because they're just so freaking intense. They're going to be the largest peak on your spectra almost always. Okay, and they're nice and narrow. And again, they always sit around that same region at 7200. It does turn out that if you have something like some conjugation in that double bond, or if instead of being a ketone or an aldehyde, it was an ester, that does shift it slightly. But I mean, this is the whole range that we're giving you here is 1680 to 1740. That's pretty incredibly narrow. So all of those are going to be indicative of a carbon-oxygen double bond, so a carbonyl bond. Again, you can see the conjugation puts it a little bit south of that 1720 figure, whereas for an ester, it's a little bit north of that 1720 figure. Again, if it's a conjugated ester, pushes it south. But again, in that pretty narrow range. Okay, carboxylic acids, another one that's kind of easy to spot. And that is because you got two things to look for. One is you have something that's similar to an alcohol group absorption band, a really, really broad, really, really strong, but it's super broad, and so broad, in fact, that it ends up overtaking, this is our sp3 carbon hydrogen bond. It's like that alcohol peak is now so broad that it's merged over into this sp3 carbon hydrogen. So the OH group for carboxylic acids are very, very broad, so far that they're extending from like 22 to 36, right? So that's a huge range right there. And in addition, you'll also be able to double check because they will have that carbonyl bond as well, right? So you'll still get that 1720 very strong and nice and narrow carbonyl peak as well. Amines. So these are nitrogen-hydrogen bonds that we're sort of measuring here. And we'll be able to spot amines, two different types of amines. So primary amines, this would be something like this, a primary amine. A secondary amine is something like this, right? So the difference between a primary amine and a secondary amine are the number of hydrogens that are actually bound to that nitrogen. Secondary amines. So the characteristic is, first of all, so again, notice we're going to lay down our 3000 block. These peaks also sit sort of just north of that 3000 marker between 3350 and 3500. I honestly, having worked in organic chemistry for a while, I think that these diagrams here are a little bit deceptive in how narrow these peaks look. They tend to be kind of broad, okay? Because again, what broadens peaks is hydrogen bonding. Amines can engage in hydrogen bonding, so they're nowhere near as broad as alcohol groups, but they are still a little bit on the chubbier side, I would say. What makes them so easy to distinguish from alcohols is that they're medium, right? So they're not going to be as intensely absorbing as an alcohol group. So how do we distinguish them from a carbon-hydrogen bond? Well, they've got some broadish nature to them. How do we distinguish them from an oxygen-hydrogen bond? Because they're on the medium end of absorption instead of the strong end of absorption. Okay, and then the big characteristic difference between a primary amine versus a secondary amine is how many peaks you actually see. So in a primary amine, you will see two peaks, these like buddies right next to each other in this region. Whereas if it's a secondary amine, you will only see one. Okay, again, kind of broadish of medium absorbance in the 3350 to 3500 region. Why are there two versus one? It's not because there are two hydrogens, it's because there's two different types of stretching that they can do when there are two hydrogens. So they can either stretch simultaneously or symmetrically, or they can stretch asymmetrically. Okay, so these molecules are doing these little dances. That's why we have these two different absorption peaks for a primary amine. Okay, so then let's just do some practice here. All right. So I'm given spectra here, and then I'm going to have to identify which one of these unknowns it corresponds to. One of the first things that I would do is actually look at my list of unknowns. Let's take this molecule here, for example. What's going to be my defining feature that I'm going to be able to spot, right? Again, functional groups. And when it might be tempting to say, oh, this carbon-oxygen single bond, but that's going to be in the fingerprint region. So that's not something I'm going to be paying attention to. Instead, it's going to be either this carbon-carbon double bond, so I can look for carbon-carbon double bond, or I also have sp2 hybridized carbon hydrogen bonds. Okay, so important to remember what we can actually see with IR when we're looking at these molecules. I think I wanted to bring that up because I think everybody's eyes have a tendency to gravitate towards that oxygen and think, oh, I can spot that. We can't spot carbon-oxygen single bonds. All right, so similar for this one, we're going to be looking for an alcohol peak. Here we're going to be looking for this carbon-carbon triple bond. As well, we have this terminal hydrogen that we can look for. Here we have a carbonyl, that nice sharp carbonyl group. Here we have their carboxylic acid and a primary amine. So these are going to be the functional group patterns we're hoping to spot. Okay. All right. So what am I going to do? I'm given this spectrum, and I understand, I put something like this in front of you, very intimidating to look at. You're like, what the heck are all these lines, right? So what's my first step? I'm going to lie down my markers, right? 1600, anything south of that gets ignored. That's the fingerprint region. 16 to 1850, something will be in there if it's a double bond, right? So this is my double bond region. I'll use a different color to point out. Then we would expect 21 to 23. I would expect something in there if I had a triple bond. And then lastly, I'm going to lay down this marker at 3000. Okay, so this right here, again, going to be in just about every spectra. You see this cluster of peaks just south of 3000. This will correspond to sp3 hybridized carbon hydrogen there. I got nothing in my triple bond region, but I have this medium to weak peak going on in the double bond region, specifically at, what would that be? 1650-ish. So we're going to say 1650 inverse centimeters. It's kind of weak, maybe on the to medium, and it is nice and narrow. And then I have this weak to medium peak that's just north of 3000, so sitting at around 3100, and it is narrow. All right, so what functional group would that correspond to? I got something in my double bond region, and importantly, it's not that obviously strong carbonyl type bond. So I'm going to be able to conclude it's this compound right here, right? So this would be A. And I can again sort of convince myself that this is correct because I have my peak over here, right? And this one would correspond to the sp2 carbon hydrogen bond, which I should see here. I guess there's also one here, but yeah. Okay. So now let's pick apart spectrum B. So again, same sort of idea. I'm going to lay down that marker. I guess I'm going to choose 1500 just because it's easier to spot on this graph. To be honest, I feel like depending on the book you read, this functional group or the fingerprint region will start at 1600 or 1500. Either kind of works. Importantly, though, 1650 to 1600 to 1850 in there is my double bond region. I don't have anything in my triple bonds, and then I'm going to lay down another one at 3000 so I can spot any sort of happening in this region. Okay, so here I have this one here. This particular graph doesn't have very many demarcations, so it's kind of hard. So let's just estimate here 15, 16, 17, 18. We'll call this 1700. Inverse centimeters. It's strong and it's narrow, right? So this is, again, one of the easier functional groups to spot, and I can determine that I definitely have a carbonyl group in this molecule. So that means that I'm going to be either this or this. Okay, and what would be the defining feature between these two would be this guy here, right? This OH group. Remember, for carboxylic acids, for alcohols, we get that nice, broad, sharp peak that's north of 3,000. For carboxylic acids, it's so broad that it actually ends up running into the sp3 carbon-hydrogen bond, and that's exactly what I see here. Okay, so this, it's not going to be this compound here, this ketone. My spectrum B will correspond to this carboxylic acid. Okay, so we can keep going. So the name of the game is always the same. Lay down your lines, 1600 to 1850. I got nothing in the triple bond region, and then it's there. All right, so I here in this compound here, I see that nice, strong carbonyl group, right? This peak here, which is, just north of 1700. Whoops. It's very strong and it's narrow. So that is going to be my carbonyl group here. I sort of, this is a good example to point out, like, what's going on over here. I don't know. Who knows, right? I don't really know where that signal comes from. In an ideal world, we would only be able to see peaks corresponding to functional groups and everything else would be gone. But the truth is that there's some sort of like background noise-ish overtones sort of stuff that happens that we can't necessarily explain. So it might be tempting to get hung up on that region there. You, again, sort of like block it all off and be able to spot your key functional groups. Things that are of relatively weak absorbance, you want to try to ignore unless you absolutely need to. So here we can determine that this is compound C. Okay. So here, again, I'm going to lay it down at 1600. 1600 to 1850. If I was going to lie down for the triple bond region, 21 to 23, and then that 3000 mark there. Okay, so I obviously have my carbon sp3 hybridized carbon hydrogen bond cluster there. This is a little bit of a tricky situation here, because I see that I do have something going on in this double bonding region, but it kind of seems to be blending in with the fingerprint region, right? So I'm not too sure if that's going to be relevant yet. So then I'm going to jump to the other defining feature here, which is these two peaks, right? So these, I have this, if I can sort of just go ahead and mark where these are. Call that like 31 to 3350. They're of medium intensity and they're broad. And in fact, I have two broad right next to one another, right? These sort of like two humps. So this is the signature of the primary amine group, right? And again, let me just move this over so it's clear. This is sort of what I meant about the other slide maybe being a little bit misleading. This is a good example here. You get this double hump to the peak, but it's all sort of broadened out because of the hydrogen bonding that occurs in these functional groups. So this would be from spectrum D. Okay. All right, so then the last ones here, let's see if we can figure these out. What am I going to do? Hopefully we got the name of the game down, right? Go through and cut up your spectra into its different portions. Here's 16, whoops, let's put on these. 16 to 1850, and then 21 to 23. Move this over just because it's kind of hard to see. And then again, put down that bumper at 3000. Okay, so here I don't see anything in this double bond region. right? I guess I got that guy there, but it's pretty weak. So I'm going to try to ignore that unless that's absolutely necessary. Can't figure it out besides that. Now I see something in my triple bond region, okay? A narrow sort of, call it pretty much exactly 2100. It's on the medium end, but very narrow. So this would be a carbon-carbon triple bond, right? One that sits just at the very southern end of that region, that 2100 to 2300 region. This would be a carbon-carbon double bond or triple bond. So this is sort of making me think that this is going to be this compound here. And then I can check because I should get this signature sp3 carbon-hydrogen bond. And that's indeed what I see right here. All right, so this is going to be around 3300. It's quite strong and quite narrow. Okay, so this is E. And then the last one here, hopefully right off the bat, something jumped out at you. And that's this portion of the spectra right here. What does that signify? A broad peak between like 33 and 35. This is just this characteristic alcohol signature that we get here. So 3300 to 3500, it's strong and it's, oh, no, it's not narrow at all. That would not work. It's broad. That is the signature of an alcohol. So I'm going to think it's this guy here, and I can just verify that the only other signal I'm really going to get are my sp3 carbon hydrogens. Okay. There's a table in your book that sort of tabulates this functional group has this particular absorbance. Notice how I specifically kind of didn't use it here. I think the most important thing is to remember these lines where you need to lay down your markers for the double bond region, for the triple bond region, and then at 3000. And then from then, I think it's, I guess what I'm trying to say is don't get married to this table. First of all, you're not going to have it on the ACS exam. Second of all, beyond matching numbers, what's easier to see are these like site patterns, right? So being able to identify that this is an alcohol group, being able to identify that ugly broad peak as a carboxylic acid group, that sort of medium two hump peak as a primary amine, et cetera, okay? So I'm not saying you can't use the table in the book. I'm saying that you don't want to get married to it to the point where that's the only way that you can do these analysis, okay? Yeah, so this week we'll be doing one of those virtual experiments. I just want to make extra special clear there are 4 unknowns. Everybody's got to do 4 unknowns, which unfortunately means you're going to have to restart the simulation 4 times and listen to the dude introduce it. All right, good luck.